Hello everyone. In this video, I'm going to go over the second half of the practice test 2 questions. So for this section, using the standard deck of 52 cards, we will draw 3 cards in order and without replacement. What is the probability of getting 3 cards? And then we have all these different properties that they could have. Okay, so we are drawing in order without replacement. So that means we can use either the fundamental principle of counting or you can use the P of NR notation. Either of those are fine. Just to review, like you have this little table up here that helps you choose counting techniques. Okay, so these are your choices here. Most people tend to prefer fundamental principle of counting, which just says to multiply together the number of options for a series of decisions. So let's go ahead and do that technique. And since we're doing probabilities, each of these is going to be a little fraction. Okay, so on the top, what I want is number of ways to get all face cards. And then on the bottom, number of ways to get any 3 cards. Okay, so for fundamental principle of counting, I'm drawing 3 cards. So I'm going to need 3 numbers. And these numbers are going to be number of ways to get the first card, number of ways to get the second card, number of ways to get the third card, and then same down here, first card, second card, third card. So for the top, number of ways to get the first card, and I know it needs to be a face card. So face cards are jacks, queens, and kings. There are 12 of those in the deck. So I have 12 options for my first face card. Now, I'm drawing without replacement, so I'm not putting that card back in the deck. So when I get to my second card and I need another face card, I only have 11 face cards left to pick from. So I have 11 options for my second card. For my third card, I'm down to 10 cards now, so 10 face cards left, 10 options for my third face card. Now on the bottom, we just want any 3 cards, so this is going to be 52 options, 51 options, 50 options. So we just start with the full deck, and then we're taking 1 card out of the deck each time, so these numbers are going down. All right, and you don't need to simplify, you can just leave it like this. Let's go ahead and do the next one. So it's going to be the same way. This is on top, number of ways to get all clubs. Bottom, number of ways to get any 3 cards. Okay, so the bottom is going to be the same as what we had before. I'll just paste it. And then on the top, now we have to think a little bit. So we want to get all clubs. The first card needs to be a club. So how many clubs do we have? Well, there are 13 of each suit, so we have 13 options. Notice here it's all clubs. It doesn't say all the same suit. If it said something like all the same suit, then I would do 52 here. I would start off with any suit, but it's all clubs, so we have to only look at those 13 clubs. And then for the second card, I need to know how many options do I have for a second club. There will be 12 left in the deck. For the third number, how many options left for a third club? And there would be 11 left in the deck. So that is number 18. Now number 19. So I want to know number of ways to get all faces and all clubs. So all faces and all clubs, be a little bit careful here. You're not getting 3 faces and then 3 clubs. You're doing this in the same 3 cards. So those 3 cards need to be faces, they need to be clubs. In other words, they need to be club faces, like all club face cards. Okay? So you need to identify the cards that are both faces and clubs. And then on the bottom, it's going to be the same for all of these. So I'll go ahead and put in the bottom first. Now for the top, like I said, you need to have every single card be a club and a face. So how many cards are there that are a club and a face? There's the club jack, the queen of clubs, and then the king of clubs. So jack of clubs, queen of clubs, king of clubs. Those are the 3 club face cards. All right, so you have 3 options for that first one, and then you're going to be down to 2 options for the second one, and then down to 1 option for the last one. Okay. Maybe I will just add like a little note in here about that. Okay, so I added a little notes about that. Now number 20 is the first time that we actually need another formula. So we're being asked to do an OR event here. So for this OR event, is this going to be mutually exclusive or not? So is it possible to do both of these things at the same time? Can I have all three be face cards and all three also be clubs? Yeah, actually it is possible, because on number 19, that's exactly what we did there. So we're going to need the regular OR formula, which is like this. So we add probability of A and B, and then we do have to subtract probability that both happen. But we already have all three of these numbers from the previous questions. So our events here are all face or all club. So I'm going to do probability of all faces plus probability of all clubs minus probability of all faces and all clubs. All right, and so that is going to give me, I'm going to need the answer to 17 plus the answer to 18 minus the answer to 19. All right, and I'll just go ahead and paste these in here. So there's that one plus that one minus that one. All right, and that is number 20. Okay, 21 is all jacks. So I'm going to start back with number of ways to get all jacks over number of ways to get any three cards. So my bottom here, same as I've done throughout the problem, is these three numbers, and my top, now I have to think about how many options do I have for jacks. So there are 4 jacks in the deck, and after taking one out, there will be 3, and then after that, there'll be 2. So that is that question, not too complicated. Next question, all jacks and all clubs. So remember, we're talking about the same 3 cards. So I need the number of ways to get 3 club jacks. Like they all need to be a club and a jack. And then on the bottom, number of ways to get any 3 cards. Okay, so my bottom is going to be the same as what I've been doing. Top. All right, so I want to know how many options for the first card, and it needs to be both a club and a jack. Well, there is only one card that is both a club and a jack, so that number is going to be 1. And then once you've taken that out of the deck, you got nothing left for these second cards here. So even if you didn't realize right away that this was impossible, hopefully you would realize it after you started putting these numbers together. This is an impossible event, so the probability is 0. Number 23, all jacks or all clubs. So we can use the same formula from before, and I'm just gonna go ahead and put it here, oops, like that. And then I'll fill in what the events are. So probability all jacks or all clubs is going to be probability of all jacks plus probability of all clubs minus probability of both. Okay. So here, actually, the part that you're subtracting is going to be 0. So you can use the mutually exclusive formula here if you want to. But even if you don't use it, you'll still get the right answer because you won't end up actually subtracting anything. So it really doesn't matter in this case whether you realized it was mutually exclusive or not. Right, so this is going to be answer to 21 plus answer to, oh, did we do this one, all clubs? Oh yeah, that was 18. And then minus answer to 22. Okay, so let me go ahead and put those in. So it was this one plus 18 and then minus 0. And that is it. All right, 24 and 25 are nots. So we need the not formula, probability that an event does not happen, 1 minus probability that it does happen. And so here it's going to be probability not all clubs is going to be 1 minus probability all clubs, which I believe was number 18. So this is going to be 1 minus the answer to 18. And that is going to be 1 minus this one. Okay. And we don't need to simplify, so we can just leave it like that. Next question, extremely similar. I'm just going to like copy and paste because it's so similar. Oops, Microsoft, why you always do this to me? Somebody go work for Microsoft and make it not paste in that weird way. Okay, so the event here is not all jacks. So I want to do 1 minus the probability of getting all jacks, which that was number 21. Okay, and so I'll just paste in answer from 21 right there. Okay, so very similar technique on those two. All right, so the next set of questions is you're not going to be doing fractions or any counting formulas. We're just going to be working with these probabilities that are already calculated for us, and we might need to put them into decimal form, but that's about it. So no fractions. Okay, a certain company requires job applicants to take 3 tests, A, B, and C, and the associated probabilities are below. So we have probability of passing each one individually. We have probability of B given A was passed, C given B was passed, and then both A and C together. So first question, what is the probability of passing A and B? So here we want to go ahead and use the probability of an AND event that was given way up here, right here. So we have probability for an AND between 2 events, and we also have it when the events are independent. Now, is passing these tests going to be independent? Probably not. I mean, if you pass the first one, you're more likely to be the kind of person who studied hard and knew how to do the second one as well. So I definitely can't assume independence in this case. Knowing that someone passed one of the tests probably does affect whether you would think it likely that they pass another one. Okay, so we can't assume independence here. It's not like with coin flips or with dice rolls or something. Like one test does affect another test because it's the same person taking, if it's the same person taking both of them. Okay, so we're gonna use this formula. That's the non-independent AND formula. And so our events here are gonna be pass A, pass A and pass B. And so we're gonna do probability of passing the A, that's the first event, times probability of the second event, passing B, given that we passed A. Okay, so what are my numbers here? The probability of passing A is right here, 60%. Since I'm going to be multiplying probabilities together, I need to put this in decimal form, like that. Now, probability of passing B, given that A was passed, is right here. It's this row, 80%, or 0.80. And now you can leave it like this. It's totally fine. So I'm just going to leave it like that right there. Number 27, what is the probability of passing A or B? So now I need my OR formula, and these events are not mutually exclusive. So I'm going to use the full OR formula that looks like this, where I have to subtract the probability that both events happen. Okay, so I'm doing my events are passing A or passing B. So I'll do each one individually, add those together, and then I subtract the probability that both are passed. Okay, so we have all of this information because the first 2 things are given in the first 2 rows of the table, and then the last one is the answer to number 26. Okay, so this is just row 1 plus row 2 minus answer to 26. All right, so let's go ahead and get those numbers. 26 is going to be in a decimal form, so I need to put all these in decimal form. So it's going to be 0.60 plus 0.70 minus, and then I'll just paste the answer to 26. Like I said, you don't need to simplify these, but sometimes it can be helpful to like plug them in and make sure you got something between 0 and 1. So I think I might go ahead and actually do that. Okay, so I plugged these both in. 26 was 48% and 27 was 82%. When you think about whether these probabilities make sense or not, it's harder to pass 2 tests than to pass either one of them individually, right? So we would expect the answer here for passing both of the A and B tests to be lower than either one by themselves, which it is. 48% is lower than 60 and it's lower than 70. Now the other way around, passing one of these or the other should be easier than passing either one by itself. It's like you have a greater chance of passing A or B than just passing B or just passing A. So this 82% is higher than both of these numbers. It's just a little quick like logic check you can use. Don't worry if it didn't make sense. You don't have to know about that. Okay, number 28, are the events passing A and passing B independent? So just to remind you guys, we have 3 equations we can check for independence, and I think I'll just probably maybe do all of them if possible to give you guys a little more practice. Okay, so these are the 3 ways that we can check. So we can check any of these. All right, and let's go ahead and try doing it the first way. So way 1, we're going to check if probability of passing A is equal to probability of passing A given that we passed B. Okay, so I'm going to calculate the left side and the right side one by one, and then I will compare them and see if they're equal. So I actually don't know was this number given? Let's check and see. I know pass A was given, right? That's 60%. But pass A given pass B, I don't think that was given. Yeah, that was not given. Okay, so we actually can't do it this way. So we can't do it with way 1. But that's fun because we still have 2 more ways. So now let me try it by way 2. So I'm going to check the second event here. So pass B, is that going to be equal to probability that I pass B given that I pass A? So I think this way it is possible to check. So I'll do the left-hand side, and then I'll compare that to the right-hand side. Okay, so pass B, that was a 70% chance. Okay, and then pass B, given that A was passed, is given in the table, that is 80%. Okay, so these are not the same. Apparently, if someone knows that you passed A, you have a higher chance of passing B because it goes up from 70 to 80, which makes sense because if you passed one test, then you're probably not that bad at passing tests, so you have a higher chance of passing more tests. Okay, so these are not equal. So these are not independent. And let's go ahead and do way 3 just for funsies. So way 3, I'm going to compare whether probability of doing both, so pass A and B, is that the same as probability of passing A times probability of passing B? Of course, I already know they're not going to be equal, but let me just go ahead and check anyway for the practice. Okay, so I'll do these sides separately. So passing A and B, that was the answer to 26. And that was 48%. Okay, now passing A times passing B just by themselves, that's the first 2 rows in the table. So we're going to do 60% times 70%. And I do need to put them into decimal form in order to multiply them. So this is going to be 0.60 times 0.70. Let me get a calculator. So that comes out to 42%, 0.42. So these numbers are not the same. Not independent. All right, so that was the 3 different ways of checking. All right, number 29. What is the probability of passing A or C? So again, I'm going to use my full OR formula, not assuming mutually exclusive, because it's not mutually exclusive to pass A or C. You can do both of those. So my 2 events here for the formula are going to be pass A or pass C. And I'm going to do that by calculating probability that you pass A plus probability of passing C minus probability of both. So I hope I know a way to do both. Okay, so A and C, those are the first and the third row in the table. So that's 60% and 50%. And then the last one here, I think, is actually the last row in the table. Yeah, A and C is just given to us, 30%. Okay, so minus 30%. I guess I didn't need to put them in decimals. So this is going to be 80%, I think, if I've added correctly. Okay, so not too bad. And the last question in this section, are the events passing A and passing C independent? Looks like I forgot a quote mark there. Okay, so we have 3 different ways of checking. I think the first 2 ways are not going to work because we don't have any given information that has A and C in there. So only it looks like the last way will work. So we're going to do way 3. And so let me type that up. So we're going to check whether P of passing A and C is equal to probability of passing A times probability of passing C. Okay, so one by one, first the probability of passing A and C, that is given in the table as 30%. And next, we're going to multiply these 2 probabilities together. Passing C. Okay, so probability of passing A is 60. Probability of passing C is 50. So we got 0.60 times 0.50. And if you put that into a calculator, 50% of 60% is actually 30%. Like half of 60%. So in fact, these 2 numbers are equal. So we do get independence in this case. So they are equal, and that means the events are independent. All right. So interestingly enough, apparently A and C must be on really different subject matter, I guess, for those to be independent. All right, so that was that section. And the last questions here, the last 4 questions, are all expected value questions. So let's go through these. The first question, a bag contains 5 $1 bills, 3 $10 bills, and 1 $100 bill. If you reach in and take 1 bill, what is the expected value of money that you get? So in this case, probably the easiest way to do this is just average together all the outcomes, because they are all equally likely. So you're equally likely to get any of these bills. So let's just total the amount of money, and then let's divide it by how many bills there were. So the total money is going to be, all right, we had 5 $1 bills, so you can do it like this if you want, or you can just realize that it's 5. All right, and then we had 3 $10 bills, so 3 of these. And then we had 1 $100 bill. So you can do it like that, or if you want to like be a little more kind of fast about it, you can do it 5 times $1 plus 3 times $10 plus $100. Okay, either way you do it, let's see, you're going to end up with 135. All right, and then divide by the number of bills, which was 9, I think, to get, okay, so our final answer here is going to be 135 over 9, and that comes out to 15 exactly, so $15. All right, so if you would repeat this experiment over and over and over and over and over, the average amount of money you would get out of this bag would be $15. You can't get $15 on any given try, but that is the average amount that you would get over time. All right, number 32. I am running a game where you roll 2 dice. If the 2 dice roll different numbers, then I pay you the sum of the 2 dice in dollars. So if you roll 2 1s, you get $2. If you roll 2 3s, you get $6. If the 2 dice, oh, sorry, that's if they roll different numbers. Okay, so like if you roll a 1 and a 2, you'd get $3. If you roll a 5 and a 6, you'd get $11. Okay, so if the 2 dice roll the same number, then you pay me $30. Do you want to play this game? Okay, so the answer to whether or not you want to play this game is whether or not the winnings, the expected value of the winnings is positive or not. Because if it's positive, then you're winning on average. If it's negative, then you're losing on average. Okay, so we need to figure out the expected value of money won in this game. And there's a hint here to refer to the table of 36 possible outcomes for rolling 2 dice. So you can refer to that, or you can just make your own table. So you need a 7x7 table, and then this column over here is going to be for dice 1 or die 1, and this will be for die 2. So basically over here, this is the outcome of the first die, and this is the outcome of the second die. So you have 6 possibilities. And then inside here, die 1 is 1, die 2 is 1, that gives you a 1-1. In fact, actually, maybe we should do it not with the little ordered pairs, but with the actual prize money. So let me do it like this. Hold on a sec. Okay, I just added some labels here and like changed the size a little bit. So basically, these are the outcomes for rolling die 1. You can get a 1 through a 6. And then for rolling die 2, you can get a 1 through a 6. And then these 36 cells right here is like the outcome for both dice at once. Okay, so like this cell, for example, means die 1 was a 3 and die 2 was a 2. Okay, and over here, this would be the one where die 1 was a 2 and die 2 was a 6. Okay, so all of these are the outcomes. And then what I want to do is go through here and put the amount that is 1 in each cell. Okay, so this says if the 2 dice roll different numbers, I pay you the sum of the 2 dice. If the 2 dice roll the same number, you pay me $30. So the same number is these cells along here. So I'm going to put -30 in each of those. Okay. So that's the amount you lose if you get any of those outcomes. And then the rest of these cells, you get the amount that's the sum of the 2 dice. So like here, 1 plus 2 is $3. Sorry, I can't type for a second. Here, 1 plus 3 is $4. 1 plus 4 is $5. And so on and so forth. So you just kind of have to like tediously go through here and figure out what these all are. And I'll just pause it and do that for a second. Okay, so I've gone through and filled them all in. And now, as far as probabilities go here, each of these outcomes is equally likely because each die is equally likely to land on any of these sides. So we don't actually need to do the thing where we multiply probabilities by outcomes. So looking back at the expected value section in the info bank, look at this first sentence here. If all outcomes are equally likely, the expected value is just the average value of whatever you're trying to find the expected value of overall possible outcomes. So just like the first question here, all we really need to do is just average together all of these outcomes. Okay, so we're going to average together the 36 outcomes. All right, so I need to find the total. And so I'm just going to add up all these numbers. Like it's a little bit not that pleasant, but that's what I'm going to do. Okay. Maybe to make it like a little bit more bearable, I'll just multiply like, so for -30, there were how many of those? There were 6 entries that were -30, right? And then next there were some $3 entries. There were 2 of those. $4 entries, I think there were 2 of those. $5 entries, there were 4 of them. So I'm going to do it like this, and I'll just pause the video and do that. Okay, so these are all the entries in the table, and now I'm going to get a calculator. I'm just going to add these up. Okay, so I did all the multiplications. Hopefully I didn't make any mistakes. And now for the final result here. Okay, so the total I got was $30 positive. And now that I've got the total amount associated with all these outcomes, I'm going to take the average. So the average amount is going to be $30 divided by 36, okay, which is approximately 0.833. So approximately 0.8, sorry, I already forgot what it was, 833. Okay, so 83 cents is what we're going to go with. All right, so the question of whether you want to play this game with me, well, on average, you're going to win 83 cents. So yeah, you should play this with me. You'll lose this $30 chunk of money 1/6 of the time, but the other 5/6 of the time, you're going to win these other amounts. And that's going to come out to actually a positive average. So as far as like justifying the answer, and the final answer here is yes, you should play the game with Dr. Jensen, because on average, you'll win 83 cents per game. So you'll come out. So you'll make money. Okay, number 33. I am running another game. I have a lot of these games where you flip 4 coins. All 4 land on the same side. Or sorry, if all 4 land on the same side, all heads or all tails, then you win $2. If 2 are heads and 2 are tails, you win $1. Otherwise, you lose $1. So the hint here is write out all 16 possible outcomes from flipping 4 coins. And what is the expected value of money that you will win at this game? Okay, so I'm going to take the hint here and write out all the outcomes, and then I'll see how much money is associated with each one. Should I show you guys like a special trick of how to do this? Maybe I will. Okay, so the outcome from flipping 1 coin is heads or tails, right? Now, if you flip another coin, you get both of these outcomes. The first set with a head first. Maybe we could do the head second, but I'll put it first. And the second set with a tail first. Okay, so now we've got 4 outcomes: heads, 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 tails, tails, heads, tails, tails. I'll put them back on the same line. Now, if we add a third coin, I'm going to copy paste. I'll put a head in front of all these ones. Head, head, head. And put a tail in front of these ones. Tail, 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 tail. Now I have 8 outcomes. So those are the outcomes for 3 coins. And now if I add 1 more coin, make another copy. I'm going to put heads in front of these ones. Heads, 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 heads. And then tails, 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 tails. Oop. Tails, 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 tails. Okay, so those are my 16 outcomes. So now you know my fancy special trick for writing them all out. Maybe I'll leave them like this. The other way you could do it is you could make a decision tree where you have 4 levels. So it branches each time into heads or tails for the next coin. Anyway, somehow you can write out these 16 possible outcomes. And now I think what I want to do is maybe make a little table, not of all 16 of these, but just of the 3 things that can happen in this problem. So amount 1, there's 3 amounts that you can win, right? You can win $2, you can win $1, or you can quote unquote win, but actually lose $1. So we'll call losing $1 winning -$1. And now I'm going to look at the probability of these. And my 16 outcomes here are going to help me figure that out. So winning $2 is for getting all 4 the same way, right? So there's 2 outcomes that are like that. HHHH and TTTT. So the probability there is 2 out of 16, or 1/8. Next thing that can happen is winning $1, and that is when 2 of the coins are heads and 2 are tails. So we need to be a little more careful this time because there's multiple ways this can happen. So there's HHTT, there's HTHT, there's HTTH, there's THHT, THTH, and then TTHH. I believe those are all of them. So that is 6 ways that can happen out of the 16. Okay, which is 3 out of 8. And then finally, the otherwise. So everything else is otherwise. So there were 2 out of the 16 for this one, 6 out of the 16 for that one. So that's 8 total. So the other 8 outcomes, or 1/2 probability, is for this last situation. You could also find that out by just counting them. Like this one is neither, this one is neither, this one is neither, this one is neither. So we're just selecting the ones that aren't half and half and that aren't all 4 the same side. Did I get all of them? I think I'm missing one. Oh, this one. Yeah, so it's those 8 outcomes for the last row here. All right, so now I'm going to use the other way of doing an expected value. So I'm going to multiply each amount 1 by its probability, and then I'm going to add those up. So I'm going to do $2 times 1/8 plus $1 times 3/8, and then minus $1 times 1/2. Okay, so let me grab a calculator and do these. Okay, so I did each term one by one, and I got 25 cents about 38 cents, and then negative 50 cents. So if we add those up, we get actually positive 0.125. So the expected value of money that you will win at this game is this number right here, 0.125. And so if you have the chance to play this game, then again, you should play it because you will make money. Okay, so last question is an insurance question. So in a single year in a certain veterinarian's area, 1% of pets are injured, resulting in average costs of $1,000. 5% of pets get a minor illness, resulting in average costs of $200. 2% of pets get a major illness, which is average costs $500. And then the vet assumes none of the pets will have more than one of these problems. So basically that means like we're not going to have outcomes where somebody has $1,200 of costs because 2 of these things happened. If we had that sort of thing, it would be pretty complicated to actually do. The vet wants to offer pet insurance to cover the costs. How much should the vet charge? So to answer this question, what you need to do is figure out, you need to calculate the expected value of losses for an average pet owner. Okay? So the expected value of losses we can get by taking these percentages and these loss amounts. So what we're going to do here, I'm going to make a little table. So let's see, I think there were only 1, 2, 3, 4. Yeah, I think that's enough. So the different amounts of losses are what I'm going to put here, amount lost. So the different amounts we can lose are 1,000, 200, and 500. And then the probability for each of these. So for amount of losing $1,000, that is a 5% chance. I should probably put it as decimal form, so 0.05. Losing $200 is, oh, I'm sorry, I did this wrong. The first one is 1%. The second one is the minor illness, so that's 5%. And then the last one was 2%. Okay, and so for your expected value here, I didn't need this last column. So your expected value here of amount lost is going to be $1,000 times 0.01 plus $200 times 0.05 plus $500 times 0.02. I'm going to put that in a calculator, add it all up. So oddly enough, or maybe it's me trolling you guys because I wrote the problem, these all 3 multiplications come to $10, so then we get $30 in total. So this is the average amount we would expect a pet owner in this vet's area to lose per year due to pet illness. So the question of how much should the vet charge per year? Less than that. Okay, so the vet should charge anything less than $30. Well, okay, this is a little bit of a tricky question, right? So he needs to charge less than $30 in order for people to think this is a good deal, in order for people to prefer losing the money to the insurance over losing the money due to illness. Okay, but there's like a little catch-22 here. On the other hand, since the vet will now have to cover the losses due to illness, he needs to actually recoup at least $30 per person. So he needs to charge at least $30 in order to not lose money, right? So there's a little catch-22 here. People won't pay for the insurance unless it's less than $30, but he has to charge at least $30 in order to not lose any money. So this is the funny thing about how insurance works, is if everybody agrees on what the risks are, there is actually no way to make money at it. But if you think about it, like he has to pay somebody probably to administer the insurance to keep track of the claims and stuff. So actually he needs to charge more than $30 because he's got to employ people to do that. So yeah, that's the weird thing about insurance is you usually end up paying more than it's really worth just for that like peace of mind. Only option here, I guess, is exactly $30. Okay, if you guys want to become actuarial scientists, that is an awesome career that I've always heard is really interesting and fun, and you can learn all about the insurance industry. So that's the end of these practice questions. If you have any questions about them, send me an email, or you can come to my office hours. See you guys later.